Imagine a world so cold that temperatures plunge far below anything experienced on Earth. A planet where frozen gases drift silently across its surface under a distant sun. Astronomers recently discovered this frigid planet, pushing the boundaries of our understanding of planetary systems and revealing the extremes possible in our galaxy. Despite being light years away, scientists can study this planet using advanced telescopes and infrared imaging, allowing us to explore environments once thought impossible. The discovery challenges conventional ideas about where planets can form, showing that extreme conditions can exist even in distant, dark corners of space. Temperatures on this planet are so low that common gases, like nitrogen and methane, freeze into solid layers, creating an otherworldly landscape unlike anything on Earth. Surprisingly, this planet orbits a star so faint that sunlight barely reaches it, emphasizing the remarkable adaptability of planetary formation processes. Studying such a cold world helps scientists understand how planetary atmospheres behave under extreme conditions, providing insights into weather, climate, and chemistry. Observations suggest that the planet's frozen surface may include ice structures thicker than anything found in our solar system. The extreme cold slows chemical reactions, meaning the planet's atmosphere and surface could remain unchanged for millions of years, offering a glimpse into primordial processes. Discovering planets like this expands the search for exoplanets, showing that planets exist in far more diverse environments than previously imagined. The coldest planet challenges scientists to refine detection methods, since standard observations often rely on heat signatures that are almost non-existent in such frigid worlds. Despite the darkness and distance, careful measurement of infrared radiation allows astronomers to calculate the planet's temperature and atmospheric composition. Interestingly, the planet's extreme cold could help preserve molecules that would otherwise break down in warmer environments, offering a natural laboratory for chemistry. This opens up possibilities for studying chemical processes in ways that are impossible on Earth, providing clues about planetary evolution. The planet's size and mass suggest that it is a gas giant, yet its low temperature freezes even the lightest gases into a solid state near the surface. The planet is so remote that it challenges our imagination, orbiting its faint star at a distance where sunlight barely provides any warmth. Its discovery was made possible through careful analysis of faint infrared signals, demonstrating the precision and power of modern astronomical instruments. The frigid world helps scientists model extreme climates, offering insights into how planets respond to minimal stellar radiation and near-freezing energy input. Observations also indicate that the planet's atmosphere may contain complex molecules preserved in ice, suggesting chemical diversity even in extreme conditions. Understanding these processes could shed light on the formation of other distant, cold exoplanets that remain hidden in the galaxy. The planet's slow orbit around its faint star means years last far longer than on Earth, making seasonal changes extremely gradual, yet scientifically fascinating. The extreme cold may also influence wind patterns and atmospheric circulation, creating phenomena unlike anything observed in our solar system. Some regions of the planet could be completely frozen year-round, while other areas experience subtle shifts due to distant solar radiation. These variations make the planet a unique case study for climate modeling in environments far beyond our solar neighborhood. Its frozen surface and atmosphere act as a time capsule, potentially preserving chemical signatures from the planet's formation billions of years ago. Discovering and studying such planets allows scientists to test models of planetary formation and stability in the most extreme conditions imaginable. The planet's distance and faint radiation challenge our understanding of habitability, emphasizing that planets can exist far beyond traditional Goldilocks zones. Even though life as we know it is unlikely there, its chemistry may resemble that of icy moons or comets within our own solar system. Studying frozen planets helps scientists understand processes that could occur on the outer edges of solar systems, including ours, offering comparative insights. Observations reveal that the planet's atmosphere is thin and cold, yet surprisingly complex, with frozen layers forming dynamic structures over time. The combination of low temperature, frozen gases, and distant orbit creates conditions where standard models of planetary atmospheres must be adjusted. Each new discovery like this improves our understanding of the variety of planetary environments possible in the universe. The extreme cold of this planet challenges scientists to rethink how planetary atmospheres behave when temperatures approach absolute zero, revealing physics in conditions far beyond Earth. Even the slightest warmth from its distant star struggles to penetrate the dense, frozen layers of gas and ice that cover the planet. Observations suggest the planet's frozen surface may contain intricate ice structures, shaped by winds, minimal sunlight, and long-term seasonal cycles over thousands of years. Its slow orbit around the faint star means that any year lasts far longer than an Earth year, making climate changes gradual yet scientifically fascinating. The frigid environment allows certain molecules to remain stable for millions of years, preserving chemical signatures that provide insight into planetary formation. This preservation is invaluable for researchers studying how planets evolve in low-temperature conditions and how atmospheres can maintain complexity despite extreme cold. Interestingly, the planet's size and composition suggest it is a gas giant, yet frozen gases like methane and nitrogen form solid layers near its surface. Detecting such a distant and cold planet requires sophisticated infrared technology, as traditional observation methods rely on heat signatures that are almost non-existent here. Infrared telescopes measure faint radiation emitted by the planet, allowing astronomers to estimate temperature, atmospheric composition, and even surface features indirectly. By studying these signals, scientists can infer how frozen atmospheres behave and how planetary weather systems might operate under such extreme conditions. The planet's remote location also provides a natural laboratory for studying celestial mechanics and gravitational effects in low-energy orbital systems. Its faint star provides just enough energy to influence subtle changes in atmospheric motion, demonstrating the delicate balance between energy input and planetary stability. Wind patterns on the planet may be slow yet persistent, gradually reshaping the icy landscape over millennia and forming unique geological structures. Researchers are particularly interested in how frozen gases interact with the atmosphere, creating layers that influence temperature distribution and chemical behavior. This extreme environment also challenges existing models of planetary formation, showing that gas giants can exist far from their stars in stable orbits. The discovery expands the known diversity of exoplanets, emphasizing that planets can form and survive under a wider range of conditions than previously imagined. By comparing this cold planet to icy moons and distant solar system objects, scientists gain insight into similarities and differences in planetary evolution across the galaxy. Its low temperature allows ice and frozen gases to remain stable over extremely long periods, creating opportunities to study chemical reactions in suspended or slowed states. Some of these frozen compounds could provide clues about how organic molecules form and persist in harsh environments. Observations of the planet's orbit reveal that gravitational interactions with other celestial bodies may subtly influence climate and atmospheric dynamics over time. Despite its distance, the planet's discovery helps refine methods for detecting faint, cold exoplanets using indirect measurement techniques like infrared and spectral analysis. Its frigid atmosphere may also reveal chemical diversity unexpected in such environments, offering insights into planetary chemistry under extreme conditions. By modeling this planet's atmosphere, scientists can test theories about gas behavior heat transfer, and ice formation in environments far colder than Earth. The coldest planet also challenges assumptions about habitability zones, demonstrating that planets can exist far from their stars while remaining stable for billions of years. Though life as we know it is unlikely, understanding the planet's chemistry provides context for studying icy worlds in our own solar system and beyond. Researchers are intrigued by potential seasonal changes, which could create shifting ice formations and subtle atmospheric variations across the planet's surface. These patterns may help scientists understand long-term climate stability on distant, cold worlds and inform comparative planetology studies. Studying frozen exoplanets offers insights into how planetary systems can survive in extreme conditions, expanding knowledge of galaxy-wide planetary diversity. Its extreme environment may preserve ancient molecular structures, acting as a time capsule for studying planetary and chemical evolution. By observing how frozen gases interact, scientists can better understand atmospheric layering, chemical reactions, and the influence of distant stellar radiation. Scientists are particularly fascinated by the planet's atmosphere, where frozen gases form distinct layers that reveal how chemistry operates in ultra-cold, distant environments. Observations suggest that nitrogen, methane, and other gases freeze into ice, creating complex structures influenced by gravity, wind, and minimal stellar energy. The planet's orbit is so distant that seasonal changes occur extremely slowly, allowing researchers to observe long-term atmospheric trends over decades. Its frozen surface may feature ice ridges, dunes, and stratified layers, offering clues about geological processes under extreme cold conditions. By studying these structures, scientists can compare planetary formation and evolution with icy moons and exoplanets across the galaxy. Even without abundant sunlight, subtle energy inputs create dynamics in the frozen atmosphere, providing natural laboratories for studying low-energy weather systems. Temperature variations are minimal but critical, as small differences influence wind patterns, ice formation, and gas movement over time. The extreme cold preserves chemical compounds for millions of years, allowing researchers to study reactions that would occur too quickly on warmer worlds. Understanding these processes can inform models of chemical evolution on distant planets and moons, and even in the early solar system. The planet's frigid environment highlights the resilience of planetary systems, demonstrating that stability can exist in conditions once considered impossible. Scientists are also investigating whether frozen compounds on the surface might include complex organic molecules preserved over long timescales. These molecules could provide insight into prebiotic chemistry and the potential for chemical diversity in cold, distant environments. Researchers study the planet's infrared radiation to determine temperature distribution, atmospheric composition, and energy flow across its surface. The remote location requires advanced instruments and careful modeling to differentiate the planet from background cosmic signals. Discovering and monitoring such planets helps refine techniques for finding other extreme exoplanets with similarly faint signatures. Its extreme cold also provides a benchmark for studying the physics of gases and ice at temperatures far below Earth standards. By comparing with Earth and solar system moons, scientists can understand how universal physical laws operate under different environmental conditions. The planet challenges assumptions about where gas giants can form, showing that distant, frigid orbits are not only possible but stable. Its atmosphere may exhibit slow, subtle circulation patterns driven by minimal stellar energy, offering insight into low-energy planetary climates. The frozen surface and layered gases act as a natural archive, preserving evidence of environmental and chemical changes over millennia. These preserved layers allow scientists to model how planetary surfaces evolve under extreme cold, low pressure, and minimal light. The planet's study informs understanding of icy exoplanets, which may be far more common than previously thought in the galaxy. Despite being inhospitable to life as we know it, the planet's chemistry offers clues about the potential diversity of environments in the universe. Observations suggest that ice formation and frozen gas layers interact with subtle wind and temperature shifts, creating patterns unique to ultra-cold worlds. By modeling these interactions, researchers can test predictions about chemical and physical processes in low-energy conditions. Its orbit around a faint star means the planet experiences minimal energy input, emphasizing how distance from a star affects planetary climate. Studying these dynamics helps scientists understand atmospheric stability, ice formation, and energy distribution on frigid planets. The planet provides a natural laboratory for observing processes that would otherwise be impossible to recreate on Earth. Researchers can examine how gases behave when frozen, how ice layers form and shift, and how subtle energy sources drive slow dynamics. These insights contribute to our understanding of planetary evolution, including early solar system conditions and the behavior of distant exoplanets. Scientists are exploring how gravitational influences from nearby celestial bodies might affect atmospheric and surface conditions over long timescales. Such interactions can provide context for orbital stability, energy distribution, and long-term chemical changes on cold planets. The planet's frozen chemistry may offer analogs to icy moons like Europa or Enceladus, where low temperatures preserve important chemical compounds. Observing the planet encourages the development of new technologies for detecting and studying faint, distant, cold celestial objects. Scientists have also been fascinated by how this frozen planet interacts with its faint star, revealing subtle patterns of energy transfer and atmospheric response over long time periods. Despite the extreme cold, minor seasonal changes may occur, causing slow shifts in ice layers and frozen gases that reveal the planet's dynamic nature. Observing these slow transformations allows researchers to understand how planets maintain stability even with minimal stellar energy. The planet's frigid environment demonstrates how extreme conditions can preserve chemical signatures for millions of years, acting as a natural time capsule. By studying these frozen layers, scientists gain insights into chemical evolution and atmospheric behavior on ultra-cold exoplanets. Its distant orbit challenges assumptions about planetary formation, showing that gas giants can form and survive far from a strong energy source. The extreme cold also allows researchers to study atmospheric layering in unique conditions, informing models for other icy worlds in the galaxy. Even subtle winds and gravitational influences can shape the planet's ice formations, offering clues about long-term environmental stability. Each observation contributes to understanding how frozen exoplanets sustain their atmospheres, surface structures, and chemical diversity over time. The planet's frozen chemistry may even provide analogs for understanding icy moons in our solar system, like Europa or Titan. Studying this planet demonstrates that temperature extremes do not prevent chemical complexity, emphasizing the diversity of environments in the universe. Its frigid atmosphere acts as a natural laboratory, allowing researchers to test theories about frozen gas dynamics and ice chemistry. By examining interactions between frozen layers and minimal stellar energy, scientists can model processes that are impossible to replicate on Earth. These studies inform understanding of energy transfer, atmospheric circulation, and chemical preservation on distant, ultra-cold worlds. Observing slow changes in the planet's frozen surface reveals long-term effects of climate dynamics under extreme conditions. Even minor variations in temperature can influence ice structures and atmospheric behavior, providing valuable data for planetary science. Researchers are exploring how gravitational influences from nearby celestial bodies affect the planet's orbit, ice layers, and atmospheric motion. These interactions help refine models for predicting stability and chemical evolution in low-energy planetary systems. The coldest planet also inspires innovation in detection technology. as infrared imaging and spectral analysis are essential for observing faint, distant objects. Its discovery highlights the importance of international collaboration, advanced instruments, and long-term observation in modern astronomy. The planet's extreme cold provides a benchmark for studying atmospheric behavior, chemical preservation, and planetary dynamics in frigid environments. By comparing its properties with icy exoplanets and moons, scientists can better understand the limits of planetary formation and stability. Subtle energy inputs from the distant star create slow atmospheric motion, helping researchers study weather and climate in near-absolute zero conditions. Ice ridges, frozen dunes, and layered gases reveal how geological and chemical processes interact under ultra-cold conditions. These frozen formations act as records of planetary history, showing how environmental and chemical changes accumulate over millions of years. Studying them improves understanding of long-term stability, chemical evolution, and ice dynamics on frigid planets. Observations also provide insight into how planets with minimal energy sources maintain complex atmospheres and stable orbits. The coldest planet serves as a natural laboratory for testing models of planetary climate, chemistry, and orbital mechanics. By examining energy transfer, atmospheric layering, and ice dynamics, scientists can predict the behavior of other extreme exoplanets. The planet's slow seasonal changes allow researchers to observe patterns over long periods, offering unique data for comparative planetology. Even minimal energy from the distant star can influence frozen gases and ice layers, creating subtle yet observable effects. Its frozen landscape provides evidence of chemical interactions and atmospheric dynamics that would otherwise remain hidden in warmer environments. Scientists also study how minor gravitational perturbations shape ice structures and atmospheric behavior over long timescales. Observing this planet expands knowledge of extreme climates, highlighting the resilience and diversity of planetary systems. Each discovery emphasizes how planets can survive in environments far colder than previously considered possible, reshaping theories of planetary formation. The planet's frigid chemistry. The coldest planet teaches us valuable lessons about the diversity of worlds, reminding scientists that planets can survive and evolve under conditions far beyond Earth's familiar environment. Its frozen surface and layered atmosphere provide a natural laboratory for studying chemical preservation, ice dynamics, and long-term stability in ultra-cold climates. By examining these processes, researchers can better understand how distant exoplanets maintain complex structures despite minimal energy input from their stars. Observations of subtle ice shifts and frozen gas interactions reveal long-term changes that inform planetary climate models across the galaxy. The planet's extreme environment challenges assumptions about habitability, showing that stability and chemical complexity can exist far from traditional Goldilocks zones. Researchers are particularly interested in how preserved molecules may inform our understanding of prebiotic chemistry and potential chemical diversity in frigid conditions. Each discovery encourages the development of new instruments, observational techniques, and models to detect faint, cold planets invisible to traditional methods. Its slow orbit demonstrates how planets in low-energy systems experience gradual seasonal changes, offering insights into long-term atmospheric dynamics. Ice formations on the surface act as historical records, revealing how environmental and chemical factors have shaped the planet over millions of years. By studying these layers, scientists can infer processes like frozen gas deposition, subtle circulation, and chemical preservation in ultra-cold environments. The planet serves as a benchmark for comparing other icy exoplanets and distant moons, helping classify planets based on temperature, composition, and energy input. Even minor gravitational influences from nearby celestial bodies can subtly affect ice layers and atmospheric structure, highlighting the interconnectedness of planetary systems. Its discovery inspires curiosity, encouraging researchers to explore how extreme environments influence planetary evolution, chemistry, and long-term stability. By analyzing the planet's properties, scientists gain insights into the limits of planetary formation, survival, and chemical diversity across the galaxy. The extreme cold slows atmospheric motion, allowing unique patterns in ice and gas to persist over millions of years, creating a natural record for study. Researchers use infrared imaging and spectral analysis to detect faint emissions, revealing temperature distribution, chemical composition, and frozen structures. Studying these emissions informs models for planetary atmospheres, ice dynamics, and energy transfer in low-light, low-temperature conditions. The planet demonstrates that frozen worlds can maintain complex atmospheres and chemical layers even without significant sunlight or warmth. Its frigid environment provides insight into low-energy weather systems, frozen gas behavior, and ice chemistry over geological timescales. By comparing its features to icy moons in our solar system, scientists can explore similarities and differences in chemical and physical processes. The planet's discovery encourages global collaboration, combining expertise, technology, and observation to expand our understanding of extreme worlds. Its distant orbit highlights the importance of precise measurement and modeling to study planets with minimal energy input. Observing slow changes in ice and atmosphere allows researchers to explore the limits of chemical stability and physical behavior in ultra-cold climates. Each observation contributes to refining theoretical models of planetary formation, frozen chemistry, and orbital dynamics. The planet's frozen landscape preserves chemical structures that may provide insight into processes occurring in other distant exoplanets. By monitoring the planet over time, scientists can understand how frigid environments respond to minor energy fluctuations and gravitational influences. Its study expands knowledge of planetary diversity, revealing how conditions once thought impossible can still support stable, complex atmospheres. Researchers explore how ice layers and frozen gases interact, shaping both surface and atmospheric properties in extremely cold conditions. These insights help scientists model climates, chemistry, and stability on other ultra-cold exoplanets and moons across the galaxy. The planet demonstrates that extreme distance from a star does not prevent the formation of stable, layered atmospheres and frozen surfaces. Observations reveal subtle seasonal changes, frozen gas deposition, and long-term atmospheric patterns unique to ultra-cold planets. Studying these features helps refine predictions about other faint, distant planets and their physical and chemical behavior. The coldest planet discovered illustrates the resilience of planetary systems and the diversity of worlds in Sene.